Hey everybody, it's Mrs. Ottmeyer, and we are going to get started today on our first AP Chemistry lecture. I know I am super excited, and I hope that you are too. So today we are going to introduce you to the kind of basics for your parts of the atom we're going to go over first, and then we're going to talk about average atomic mass and the technique called mass spectroscopy or mass spectrometry. So we're going to kind of click through, and hopefully it's pretty easy to figure out. If you have any questions, obviously make sure that you post them in the Google Classroom post or send me an email or meet with me in Google Meet. All right, so just as a review for you to remind you, there are 3 subatomic particles in an atom. There are protons, which are positive and are located in the nucleus. There are electrons, which are negative and which are located outside of the nucleus in that cloud kind of around the outside of your element. And then there's the neutrons, which are in the nucleus as well. And neutrons are a neutral charge that essentially are like glue that keeps positive proteins from flying away from each other. Because if you take a positive and you put them together, they're going to repel. So once you start to get enough protons, you need some neutrons to kind of act like a buffer to make those protons still stick together. As a review for you, on a periodic table, which you should be getting a new copy of soon, you will see on the periodic table squares a number at the top, which is called our atomic number. The atomic number represents for a neutral atom the number of protons and the number of electrons. It is always going to be the number of protons, but the electrons, remember, can either be taken away or more can be added. If you have electrons that are taken away, you get a positively charged ion called a cation. And if you add electrons from another element, you're going to have a negatively charged element or ion called an anion. So just kind of some terms to refresh your memory. But if you take a look here, our atomic number represents most of the time the number of protons and the number of electrons. Chemical symbols you should be familiar with and the name. And then down here at the bottom is our average atomic mass or atomic mass. And when we do mole calculations, we typically use that mass number. It's something that you've used a ton in your previous chemistry experience. But as a refresher to you, when we talk about the mass of an atom, the mass of the atom comes from the number of protons plus the number of neutrons in the nucleus. We leave out the electrons because the electrons have a mass that's like 10,000 times smaller than your proton or your neutron, and so we don't include them. And their mass, what we do to record them, we use something called an AMU or an atomic mass unit. Now, an atomic mass unit is a made-up number that is used to kind of make the masses of these really teeny tiny things more manageable. I believe that the mass of a proton is like in the factor of something times 10 to the negative 27th kilograms. So it's like super tiny. I just, can't even imagine the amount of calculation errors we'd have if we had to type those in. And so what they do is they just say, hey, this is 1 AMU. Makes life easier. So what happens is if we want to figure out the mass of a particular atom, what we do is we add up the protons and the neutrons. And so in theory, when you do that, you end up with a whole number. Like, for example, there is an element of iron that has 26 protons and 28 neutrons. And so when you add those two things up, you should get a mass of 54. You have the same thing for a different type of iron atom where it has 26 protons and 30 neutrons, and that has a mass of 56. However, this guy here becomes kind of problematic because you've got this mass that's this, neither of those numbers. It's not 54, it's not 56, it's not a whole number at all. And the reason why we have this average atomic mass here at the bottom as a decimal is because of the fact that there are different isotopes that exist for iron and almost every other element that we see. So what ends up happening is that an isotope is an element that has the same number, I should say 2 isotopes are elements that have the same number of protons but different numbers of neutrons. So this would be the isotope iron 54. This would be the isotope iron 56. And so there are actually several more isotopes of iron, but I just picked the most common ones. And what we do, if you kind of remember, is we do a weighted average that takes into account how much of that particular element we have. So, like I said, the atomic mass is the sum of the number of the protons and neutrons in its atom. Different isotopes exist for each element. And then, like I said, the average atomic mass is calculated using something called the abundance of an element. The abundance essentially is just the percentage of each element that we have present in the world. And the way that we calculate that or figure that out is using a machine called a mass spectrometer. So what a mass spectrometer does is it takes a sample of an element and it runs it through this kind of tube, which you can see on the screen here. And what they do is they take a sample of that element and they heat it up hot enough so that that element turns into a gas. When you turn it into a gas, then they strip off electrons and turn those particles into cations or positive ions. And so they run them through the ionization chamber after they turn it to a vapor, and then they take them, accelerate them, and then they run them through a really strong magnet. I'm going to actually kind of flip through one more slide because I think this slide does a better job of showing it. So again, the gas enters the sample. They run it through a coil that ionizes the gas. This is all of the particles that you see when you take them and you ionize them, and then they run them through a slit. And then the slit has all of these particles that go past, and then they run past this big, strong magnet. So when I like to explain average atomic mass, what I do is I think about, like, let's say you went around and you know, because, you know, you're bored, I guess, you ended up finding a dumpster full of balls. And that dumpster had bowling balls in them. It had basketballs and it had ping pong balls. And it's legit like a big dumpster. And because you're bored, you then took all of the balls that you got and you ran them down a big hill. Maybe like the big hill here at Lincoln. Okay. So you do that. Imagine that the bowling ball, the basketball, and the ping pong ball are three different types of isotopes of an element that you have in a sample. One that's heavier, one that's middleweight, and one that's a lower weight one. So you take this big dumpster, run it down the hill, and then because also mischief, you've got a fire hose. So you found a fire hose. What you do then is you take the fire hose and shoot it perpendicular to the balls rolling down the hill. So if this is my hill, okay, I'm shooting a fire hose perpendicular to that. So stop, I guess, mentally picture what's happening there, and then think about what that's going to look like if I take a fire hose and shoot it towards these balls rolling down the hill. Think for a second about what's going to happen. Okay, in your mind, which one of them is going to be affected most by the fire hose? The ping pong ball, the basketball, or the bowling ball? Hopefully in your head, you're thinking, oh, the ping pong ball is going to get shot way more or angled off way more because it's lighter. And that's exactly correct. And it's exactly what happens with a magnet. So if you think about this magnet here, the magnet is sending forces to try and knock these particles off track. And what happens is the particles that have a lower mass, those get knocked more off track and curve more than the particles that are heavier. So if these are two ion streams, the ions that are lighter are going to curve more than the ions that are heavier. And why that's advantageous is then we can set up a recording device here. And in this picture, you can kind of see I have a red track, a green track, and a blue track. What happens is you can adjust this recording device, and then what it does is it essentially provides a count for how many particles hit this particular recorder. And so what you can do is kind of adjust the machine for different masses, and then it records the abundance of each of the types of particles that you have. So you get this count, and then we turn that count into a percentage. You will see the isotopes put into different kinds of like organizational categories for their abundances, and these are kind of the two ways that you can see them. So for the lithium isotopes that you see on here, we've got lithium 6. Lithium 6 is 3 protons and 3 neutrons. Atomic mass in U, which is AMUs, is 6.02. Natural abundance is 7.5%. So what that means is that of all of the lithium ions that they run through that machine, 7.5% of them are lithium 6 isotopes. On the other hand, the lithium 7 isotope, which is the other isotope of lithium that we have, has a mass of 7, and it's 92.5% abundant. So that means of all the lithium atoms that we tested, over 90% of them are lithium 7, and 7.5% of them are lithium 6. The other way that you could see the data presented is something like the chart that we have down here. So in this particular chart, you can see that there are isotopes at 84, 86, 87, and 88. And then what you're expected to do is you are going to take those bar charts and read them to figure out the rough abundances. What we're going to do then is in the next video, I'm going to show you how you can kind of roughly predict what an average atomic mass is going to be, and then we're going to run through a sample problem. If you have any questions, make sure that you hit me up in a meet, and we'll see you in the next video.